Little extremely sorry for the participants for the small delay.
Thank you all.
So we now move to another lecture. So by Professor Ankit Garg. Remya, do you want to introduce?
Yes, my pleasure. I'll be here.
Okay.
Am I audible?
Yes, you're audible.
Yes. Okay, so without much delay, we will move to the third session of the day. So to deliver this session, we have Professor Ankit Garg with us. Professor Ankit Garg is Associate Professor in Civil Engineering at Shantou University, China. Prior to joining Shantou University, he served as Assistant Professor at IIT Guwahati and as a part-time World Bank consultant for monitoring transport infrastructure projects in Assam. Dr. Garg received PhD from Hong Kong University of Science and Technology under Hong Kong PhD Fellowship Scheme. He pursued his BTech in Civil Engineering from IIT Guwahati. Dr. Garg's research focus is on development and utilization of sustainable materials like biochar and fiber, also includes the vegetations for geo-environmental applications. His research group has been mentioned as the highest number of publications and citations in Web of Science in research related to green infrastructure from 2010-19. He's also currently guest editor for the special issue related to Internet of Things and Artificial Intelligence in Geotechnical Engineering in Journal of Rock Mechanics and Geotechnical Engineering. Dr. Garg has several awards to his credits, which include the prestigious Telford Premium Prize for 2020 from British Civil Engineers Association for publication in Geotechnic Letters, UK. Besides, he has also awarded with Shantou University Excellent Young Talent Program, Talent Youth Scientist Program, Young Doctor Award from Ministry of Education, Guangdong, and International Scientist Exchange Program. He is currently preside over National Natural Science Foundation of China Youth Project on Vegetation for Soil Remediation. Dr. Garg has already delivered several lectures at various universities across the globe like UK, Japan, Germany, Macau, Taiwan, and Thailand. With this brief introduction, let me welcome Professor Garg to our session, and the floor is yours. You may please take over.
Thank you, Dr. Remya. Thank you, Dr. Rao, for this wonderful opportunity. And I think this is last lecture for today's session, and I think it's already getting a bit late.
One more lecture.
Okay, so there is one more after this. Okay, I'm sorry. So I will try to be within my timeline. And also regarding presentation, my presentation will be more towards fundamental aspects related to soil water retention and erosion aspect of using biochar. Biochar I will introduce during my lecture. What is this material about? How we can utilize such material in our landfill liners or even in green infrastructure, as I think Professor Saradas also mentioned in his previous lecture about phytoremediation. So we can utilize such material in such systems to enhance their performance. So before I go into details, just to give you idea of Shantou University, because Shantou is not as popular as Beijing or Shanghai, so it's located very near to Hong Kong city of China. And usually we used to have direct flights from India to Hong Kong, and from Hong Kong to Shantou it's usually 2 hours by high-speed train. And we are working on green infrastructure projects in our university. One of the project is also on vertical forest. So which is basically a high-rise building. You can say about like 100 floors, and each balcony is planted with several trees. So that is a kind of a concept. We call it the vertical forest, which has been already, I think, was initiated in Italy and now is expanding in China. And other than that, we work on soil plant atmospheric interaction that is related to green infrastructure. So we timely invite also students from India. I mean, before pandemic, it was very common from India, from different IITs to visit us. I mean, in both PhD and also in master and undergraduate level. So coming to the presentation, erosion in landfill sites are also not very uncommon. It's common, And there is a recent history about news about several landfill sites in England, which are also susceptible or vulnerable to coastal erosion. And because of this erosion, these waste are left exposed to atmosphere, so which increases also chances not only, I mean, of gas leakage, but also at the same time of leachate generation and transportation. And in addition, it also destroy ecology, that is local animals and plants. So for this erosion, one of the methods I think which researchers have used before or even in practice is about using vegetation. So in vegetation, they mostly make use of grass, which with a deep rooted grass like vetiver or could be Cynodon dactylon. And we know, I think from yesterday's presentation also, that one of the focus of our, I mean, in this system of landfill liner is if we can try to enhance the performance of the top layers, like which could be surface layer containing vegetation and also the protection layer. And I think this material biochar, although it looks like charcoal, but it's not charcoal. It has been done research quite extensively before. I think Professor Krishna Reddy has done a lot of pioneering work in it, specifically from the perspective of methane oxidation, that this material, biochar material, is quite useful for methane oxidation. However, its interaction with atmosphere from context of unsaturated soil mechanics like water retention, soil water retention, cracking, and also about erosion is not investigated much. And another thing is when we have to think about using this material in our landfill liner, we also have to think from the production point of view, because this biochar material is not unique or is not very specific. Even if we produce from the same waste, these properties can vary quite significantly. So it's not very uniform material or homogeneous. So for this, we need to very carefully choose production process also, which can specifically meet the requirements of our geotechnical engineer. So in literature, most of the studies which has been done is based on material which is directly bought from the market. Okay, so for this we need very specific studies in our laboratory where we can control the production of this material to see whether it meets the requirement of our geotechnical engineers. So I mean, we can also use the waste to generate this biochar material, but as I said, we need to be very careful. So depending on the waste type, the properties of biochar will vary quite significantly. And how biochar looks, on the left side, if you see, it looks like charcoal, but it's not charcoal. And the scientific definition is it's a material which is obtained from thermochemical conversion in limited oxygen environment. So limited oxygen environment is very important. And chemically, it looks like the picture in the middle. So it has porous structure, like you can see those white pores in the middle. And also it has functional groups on the surface. So these functional groups can be hydrophilic and hydrophobic. And the activity of this biochar depends on porosity and the activity of the functional groups. So in charcoal, the problem is that in charcoal, it's produced mostly at very high pyrolysis temperature. It could be around 1000 or above. And when you produce charcoal at very high temperature, like by burning any biomass, you are losing the functionality or the functional groups. So in charcoal, these functional groups like carboxylic, phenolic, dioxin, peroxide, the functional groups are usually absent. So it is mostly a porous material. But biochar has both functional groups and porosity. So this material is not new in itself. It has been used quite extensively for soil remediation in agriculture, for carbon storage also, and also recently for energy storage. However, when we have to use in geotechnical engineering, I mean, especially landfill liners where soils are highly compacted, or in green infrastructure, we need to do very specific studies. And before I go into details, I'm not sure many of you have taken unsaturated soil mechanics in your course. I mean, as such, I mean, most of the students. So I will just give an idea of what is soil water characteristic curve looks like. Just wait. Yeah. So soil water characteristic curve is ability of, it determines the ability of soil to hold water at a given soil suction. Okay. So this is how a curve looks like. So on the y-axis is volumetric water content, or you can also denote it as also represent in form of degree of saturation, and on the x-axis is metric suction. It's a very typical soil water characteristic curve. So usually at this point, your water content is maximum. Okay, so we can consider it, I mean, in layman terms, it's considered very wet soil. So at that point, the suction is almost zero or near to zero. Okay, and when your soil is extremely dry, so this is minimum water content, very extremely dry soil, or so this is, we call it residual water content, and suction is usually very high. Okay, so this curve is known as soil water characteristic curve. Okay, so this curve actually also determines a lot of properties of our unsaturated soil, specifically even if you're talking about volumetric deformation or shear strength is also uh, affected or determined using this soil water characteristic curve. So one of the basic aim is to understand how this biochar will affect this entire soil water characteristic curve. And hence, we also know permeability or the rate of flow of water. And to give you more little bit idea from what physically it means, metric suction. So metric suction, usually in our, I mean, basic soil mechanics, we consider three different phases of material. We have air, water, and solid. But in unsaturated soil, we have additional phase of material, which we call it as contractile skin. Okay, so this contractile skin is a air water interface, which helps to hold soil particles together, and that is one reason why we can see on the left side that the castle, if you have I mean, the sand castle could stand vertically 90 degree. If you make it with the sand, which is neither very wet or neither dry. So that is because the contractile skin in the soil helps to hold the soil particles together. So that exactly the force that exists between this air-water interface, we call it metric suction or tension. Similarly, we know insects, they can float on the water surface, I mean, usually, and the strength, the air-water interface between the legs of the insect and the water is again helps insect to float on the water. So that is, this contractile skin is very thin, but it is very powerful. Okay, it's very thin but very powerful. So it is that particular thin contractile skin which is written here. So it is this skin, contractile skin. So this one you can see MC, which is actually controlling the strength. And when we talk about the strength of unsaturated soil, it actually determine the major proportion of it. Okay, but under rainfall, so what happens is under rainfall, this contractile skin tends to disappear. Okay, slowly. So that is why soil loses its strength under rainfall. So biochar material, the idea of using biochar is that we can include more porosity, and also because it has functional groups, we can increase additional water to be attached to particles to create more such kind of surfaces. So contractile skin is very, very important. As I said, it is the skin which gives us metric suction. So that's why when your soil is very wet, your suction becomes zero, almost near to zero, I'm saying. And when it's very dry, your suction is very high. And this is again one diagram illustrating how we can use biochar. So I think many of you might have read it already, that usually we can idealize soil pores in form of a capillary tube containing water in it. So the water which held in the capillary tube, I think we all know it can be denoted by 4 times tension over cos alpha over d gamma. And idea of using biochar is that this d, the diameter of pores of biochar, is usually very small as compared to that of soil. And that is one reason why this HC, or the water retention in biochars, is expected to be higher. Okay, so this is very basic idea of using biochar in soil, because it has very fine pores, and due to fine porosity, the water retention in biochar particles will be higher than that of on an average. So I'm talking about average pores, okay, size will be higher than soil. In addition, biochars have functional groups which can also increase water retention. So why we need to do research in our geotechnical engineering? People can ask that, okay, it has been done in agriculture already about soil water retention with respect to biochar. However, in engineering, the problem is that we have to think about density of soil, which is much higher in engineered slopes or landfill liners. We are talking about around at least 80 to 90% of degree of compaction. And in engineered slope, we want it to be less maintenance. We don't want to be have very high maintenance, and that's why we avoid adding of fertilizers and also irrigation. In agriculture, we usually irrigate. Another important aspect is design period. Design period in agriculture is usually very less. I mean, we usually say 2 to 3 months and you harvest crops, or it can go maximum 6 months depending on your uh, harvesting time and also your, I mean, economic, how much you want to replace biochar. But in engineer, we want it to remain it forever almost, or up to at least 20 to 30 years of our life period. And depth of influence. Also in agriculture, our depth of influence is usually very shallow. But in case of landfill liners or slopes, we can be talking about at least 1 to 2 meters on the top surface. And in agriculture, they have already researched it about the amendment ratio. You can mix biochar in terms of 0 to 5%. 5% is usually very high, but for engineered slope, depending on our requirements, we don't know currently how much is suitable. But we also need to consider about pH value that biochar can affect before we do it. So in remarks, I think biochar can have negative impact. Okay. So when I'm saying using the word biochar, again, we have to remind ourselves that we cannot generalize any results from biochar. Each biochar behaves differently. I will discuss in my presentation. So some biochars can even have negative impact on soil. Even some biochars can have negative impact on vegetation growth, which we have found in our results. So before we try to make it, I mean, put into practice, when we do our research, we have to be very, very specific which kind of biochar we need, what are the specification and guidelines. So in general, we like to propose biocover, which includes not only vegetation and soil, but also biochar. And the advantage of biochar is, of course, it provides nutrients to soil, it provides porosity, water retention. Also, it's useful for carbon sequestration and climate change. And till now, according to research, as I said, people, researchers, they have used biochar directly from the market without in-house production. So there is lack of understanding of on control of physiochemical properties, or to specifically, for example, in geotechnical engineering, if I ask which biochar, which type of biochar is useful for water retention in soil, or which biochar is not useful for water retention, or which biochar is useful for reducing crack. So for that, we need specific answer, like which feedstock type, which pyrolysis temperature, what are the production condition of biochar, so that it meet our requirements of geotechnical engineering. And at the same time, there is also lack of understanding of how biochar influence cracking and hydraulic properties of compacted soil. So this is one picture. I think it's mostly taken from energy literature. So you can look at this different type of, I mean, just an idea why each biochar is different. If you produce biochar from wood, your carbon content will be very high. It can go up to 50 to 90%. If you produce from animal waste, like manure, your carbon content can be very low. So you can understand if your production, I mean, depending on your pyrolysis temperature, even the temperature you can see, if you heat biochar, make biochar at very high temperature, your carbon content is usually very high. Okay, it will increase, right? So depending on your production process, you can change the properties of biochar in such a way that it meet the needs of our geotechnical engineers, whether we have to reduce cracking, whether we have to increase water retention, or we have to reduce erosion. So it means we need specific guidelines to choose biochar also. And again, to give you more idea, we don't have to see the entire slide, but just focus on this part. If you look at this, how biochar is produced from biomass when we heat it, so it produces char. So this material looks like this. And if you further heat it, if you increase the temperature, you can see these functional groups, which is these groups, they disappear. So it makes more like aromatic structure, benzene-like structure. So this is how it looks. So when you increase the temperature, you are actually reducing the functionality of biochar and converting it into more like charcoal material without any functional groups, only porosity, only porous material. Okay, so this objective, before I discuss erosion process, so I thought about it yesterday, but I think it's important to understand first basic and uh, material understanding of how it affects water retention and cracking before we discuss about erosion. So although in objectives I have written the first part is investigate influence of biochar on erosion, but I will discuss it later after we understand that how biochar will influence unsaturated water retention curve and also cracking. So to, as I said, we need to have our in-house production of biochar if we have to investigate, understand what kind of biochar is useful for geotechnical engineering. So for this case, for our case, we focus on two waste resources. One is from algae and water hyacinth. So since Shanto is a coastal area, very close, so we have a lot of algae waste. And also we have a lot of ponds where water hyacinth is present. So this water hyacinth is also quite widely available in different parts of the world, even in India and some ponds in Assam. I think there's a very big lake in Assam, so that also have water hyacinth. It's very common in India also. So I'm not going in details of it, but just to give you idea, to verify our hypothesis of how biochar could affect water retention, we performed several experiments in greenhouse, and where we constructed a one-dimensional pot containing compacted soil. We installed suction sensors and also water content sensor and monitor this pot under drying wetting cycle for around 9 weeks. So there were around 7 drying wetting cycles. And during this, we also captured using image camera images for understanding surface cracks, crack propagation. And this is how, just to give you idea how this biochar looks like when you produce at lower temperature and higher temperature. So at higher temperature, your porosity increase of biochar. Okay, your porosity increase. However, these functional groups reduce. So these images that we took during this experiment, we did this analysis by measuring crack intensity factor. So this crack intensity factor, we develop our own program in Python language, which we also patented. So in this program, you can automatically calculate crack intensity factor by importing multiple images in one time. And to make you understand this part, so this is soil water characteristic curves that we got from this experiment for different type of soils. So this BS is bare soil. S2BC is soil with 2% biochar content. This is 5% biochar content. This is 10% biochar content. So let's take two curves, so BS and S10BC. So on y-axis is theta, means volumetric water content. On x-axis is suction. Okay, and this y-axis is crack intensity. So you can just visualize this as amount of crack. So let's look at this orange dots. So orange dot here is around 7. So this is, as I said, is bare soil, right? So for bare soil, it's around 7% cracking. But when we look at soil with 10% biochar, the cracking reduced by almost more than 2 times. Okay, it's around 3% here. Okay, and when we look at this water content, this curve, so the minimum water content is around 10% for bare soil. But when we look at the one with 10% biochar, the minimum water content could reach around very close to 20%. It's around 17%, you can say. So it means even in very dry state, during the drier state of soil, because of the presence of biochar, your minimum water content was increased, which is more critical for us, for engineers, because okay, when the soil is wet, when we have enough rainfall, we do not have to worry about vegetation growth. We do not have to worry about other things. But when your water content is minimum, that is actually a time when we have to worry about even gas flow or even about cracking and also about vegetation. So the minimum water content increased by almost 2 times, okay, with the presence of 10% biochar. And when we think about, again, when we think about maximum water content, it was around 30%, which also increased. So it means your ability to retain water increase uh, from 30 to 40%, the maximum ability, with addition of 10% biochar. When we look at 15% biochar, the difference between these two is not much. Okay, it's not very significant. So you can see still the cracking remains close to 3%, and this one also close to 45%, if you consider the error bar. So it means somewhat around 10% of biochar content, you can get maximum efficiency, okay, in reducing cracking and also increasing water retention. Now, how this is useful for in landfill liner systems is especially when our landfill liner systems are subjected to rainfall. In suppose it's in subtropical region which receives very heavy rainfall. So during wet season, the ability to retain water of the system will increase, especially in the top layer and also in the protection layer, due to presence of this biochar. And also in dry regions, even in subtropical regions, when it's subjected to, I mean, periods of no rainfall, like in India also there are many regions when there is no rainfall for long time, maybe 1 month or 2 months. During that time also, this presence of biochar, when we look at the minimum water content, it will still help to retain. So this minimum water content can help to sustain the vegetation on the that liner, okay, landfill liner, the top. This is very important because if the vegetation fails in the top layer, uh, let me back to that slide. So if the vegetation fails in the top layer, it will be also detrimental. So like this. So if this vegetation fails in the top layer, the problem is our surface or the protection layer will get exposed to the atmosphere. So if the vegetation fails, what happens is the roots get shrink and there will be lot of preferential flow of water happening from the top layer. So that is why it is very important for us. I mean, although we have done lot of research in this part and in developing this hydraulic barrier, but it is very important that we also help to sustain the top layer and the vegetation layer as well as protection layer. So this biochar can be useful to sustain vegetation growth during extreme drying periods and also during wetting periods. So that is one advantage that we can have using this biochar. Okay. Okay. Yeah. Okay. So we were here. As I said, minimum water content is important. Okay, as I said, it has increased. So biochar do have an effect. Okay. Now the question is, you can ask me, this experiment was done for 63 days. What will happen after 1 year, or what will happen after 2 years? I have not shown in this presentation, but based on literature and also research that we are conducting right now, the biochar ability to hold water actually is quite efficient even after few years of our installation or mixing. And the reason is that the aged biochar also undergoes some microbial activity, which is very slow and can further enhance water retention uh, in very slow manner over a period of time. So we do not have to worry about the aging of biochar effects here, like which I think for fibers, when we were thinking about natural fibers, I think you might have read literature. Natural fibers are vulnerable to decomposition over a long time, but biochar is not. Biochar can remain stable for over 100 years. And the reason is that uh, the fibers, they are prone to decomposition of biomicrobial activity, but biochar, since we have already thermally decomposed it from biomass, so it remains more or less stable for more than 100 years. So that's why in terms of life period for engineers, this material can sustain its efficiency for a long time. Yeah. Now the question comes is, what will happen if because this biochar that we used here in our first experiment was from water hyacinth. It's a plant. Okay. The question is, we can also have biochar which is produced from some animal waste. Okay. So you can see here. So there is animal waste which is called pig manure. Okay. So this is pig manure biomass. So using pyrolyzer, you can produce pig manure biochar. So this is wood biochar. Okay. This is mostly, you can say, lignocellulose waste. Uh, so it's not a waste. I mean, I'm just saying it's just because we can produce some valuable material. So this was supposed to be waste, but then if we can make biochar, it becomes useful. And similarly, we can also modify biochar by implementing some kind of nanoparticles like iron particles or zinc particles to make for more finer biochar. Okay, then we call it chalk white nanobiochar. So we conducted experiments in a very small scale level in laboratory, very preliminary experiments. We conducted at 4 different drying wetting cycles. Um, we used a small dish where we compacted soil and soil biochar mix. And I'm not going through details, but in terms of results, what we got was the bare soil and the animal-based biochar, they both have very high cracking intensity. I mean, the cracks were very like common in these two types of soils: bare soil and animal. And the soil with wood-based biochar will have minimum cracking. Okay, and the reason what we found was that the wood-based biochar has more porosity and also functional groups, which helps to retain more water. Okay, so in terms of also cracking, if you have to think about using, if you have to recommend biochar for usage in landfill liners, okay, even for field evaluation, okay, uh, so even in terms of field practice or evaluation, if we have to think, we have to maybe go with more plant-based or based biochars, where in regions which is more drier or also which receives very heavy rainfall, because the tendency to retain water is much higher. And the effect of increasing, so this is for 5% and this is for 10% biochar. So in 10% biochar content also, for wood-based biochar, like W, if you see this, so the cracking goes is much less as compared to that of bare soil. Okay, so the difference is much higher if we even at 10% biochar content between bare soil and wood-based biochar. So it means for engineers, if you have to think about using it in field, maybe we will go for plant-based biochars more than animal-based biochars. But there is one catch which I have not shown, is that strength. Okay, engineers also like to maintain high strength. The unlucky part is that the plant-based biochars are not good enough to maintain strength of soil as compared to animal-based biochars. When you mix biochars with soil, there is a tendency to lose strength also, which is more in case of plant-based biochar than animal-based biochars. So we have to think very carefully when we have to mix in what proportion is animal or plant-based biochar. So the areas where we are not worried about strength factors, where that we can go for plant-based biochars. But if we are going for a very steep slopes or we are going for regions with steep areas, maybe strength is very important in that part. We may have to uh, reduce dependence on plant-based biochars. And just to give you idea of mechanism, I think for students, we have used before fibers also to suppress cracks. We can use vegetation, and there are different mechanism to it. For biochar, as I said, uh, plant-based biochars are good in suppressing cracking as compared to animal-based biochar. And the major mechanism comes from functional groups and porous structure. And degradation, of course, is very, very low. I'd say it can retain up to more than 100 years. And when we talk about now, since we understand basic influence of biochar in terms of water retention, now we can go into erosion aspects, because erosion is more dynamic aspect. So it occurs, I'm talking about rainfall erosion. So during rainfall, when the water is splashed on the surface, it also causes stress on the surface particles, which makes them erode in both mechanical way and also hydraulic way. And at the same time, there is infiltration happens in the subsurface, and there is runoff. So to understand this aspect, we conducted a flume testing in a university. We designed a flume with 3 different strips of soil. One is bare soil, one is soil with 5% biochar content, one with 10%. And we subjected 3 of them at the same time using rainfall simulator. So it's a very basic thin strip of soil. You can imagine where we are simulating very top shallow surface of the liner or a slope. And we conducted, we collected water flow from subsurface and also from runoff. At the same time, we also filtered sediments which are coming out from in this flow. Because biochar is very small, fine particle, we expected a lot of biochar to be washed away during this rainfall. And for this experiment, we varied rainfall intensity, gradient, and length. So we have two different gradients, which we consider to be shallow, not steep slope, because in landfill liners or cover, we are not expecting too steep. So maybe 7 to 20 degrees, which are relatively flat. And rainfall intensity also we varied from 60 to 90 per hour, which is relatively high intensity rainfall. So what we found is that if you have high biochar content, so your runoff in general reduces. Okay, um, and also in terms of erosion rate, also it reduces quite significantly. Okay, but when we have 10% biochar, there is little higher erosion rate, and the reason what we found is that if we have excess biochar, the problem of washing also comes into picture. It's because biochar particles are very fine, very light. The specific gravity is around, can vary between zero point 0.9 or to even 1.3. So like this. So compared to soil is around 2.67. Our soil is standard. But for biochar, it can be half of that. Okay, it could be 0.9, 1.1, 1.2. So if you have excess biochar, it could be also problematic because under even not only rainfall erosion, but also under wind, there could be problem of erosion or carrying away of these particles. So that's why we found that around 5% biochar content was quite optimum in reducing erosion rate and runoff. And the main mechanism for this is, as I said, is the formation of soil biochar aggregates, which happens because of porosity of biochar and also these functional groups, okay, which causes retention of these particles. And we also compared influence of several factors like rainfall rate, slope gradient, and slope length. So biochar content means when we have different percentage of biochar, it influences more than rainfall rate, and slope gradient has very less influence. In addition to flume testing, we also did whole erosion test. This is very basic test which can be done in laboratory, where you can take actually simulates more less on surface erosion but more of a subsurface erosion. So in this whole erosion test, we also did on different types of biochars from animal and plant origin. So this is poultry litter of chicken. This is for sawdust. This is for peanut shell. So you can see here a difference. So the poultry litter is not very porous. So sawdust, peanut shell, and water hyacinth, they have this hollow structure. Okay, hollow structures you can see, but for a poultry litter lack that structure. So it means we can expect sawdust, peanut shell, and water hyacinth maybe perform better in terms of water retention as compared to animal-based biochar. So similarly, we did this test at different density and also in different water content. So this one is -5% OMC, means dry side of optimum moisture content. This is wet side of optimum moisture content. So what we found is that uh, when we have the dry side of the uh, optimum moisture content, the erosion rate, okay, this is for bare soil, you can see. So the erosion is reduced quite significantly, okay, when we have biochar content of around 10%, okay, for all types of biochar. But on the wet side of optimum, you can see actually this biochar tends to have even the opposite effect. So it means uh, when your soil is very dry and the rainfall comes, I mean, in the subsurface flow, there is tendency that biochar can prevent or minimize the erosion rate. But if under existing, if the soil is saturated or nearly saturated, and if a rainfall comes and there is very high subsurface flow, this biochar and effect of biochar becomes very negligible. Okay, and one of the reason is that the is because of this hydrophobic groups also of biochar, which becomes quite active in repelling water, and this washing away of biochar happens. So that is one uh, area which needs to be further investigated in future, especially in the field, how erosion aspects will behave when we have biochar mixed with soil. So in conclusion, biochar in laboratory influence testing did found to have effect on reduction in erosion, and this was due to its porosity, also roughness, and presence of functional groups. Plant-based biochars seems to be more beneficial than animal-based biochars. But as I said, in field, since there are multiple processes happening, and at the same time there is simultaneous drying wetting taking place, we need to investigate this um, potential of this material in field if we have to promote. And future thoughts, all biochars are not same. When we generalize any conclusion that biochar is useful or not useful, we should be very careful that it depends on the production process of biochar. Some can be useful, but some can have even negative effect. And we need long-term interaction studies. We need to also think about how to minimize negative effect of biochars. And also we need to think about methane oxidation potential for different types of biochars. So this is one of the studies which was published recently. We and did in collaboration with in Hong Kong, I think with Dr. Bodolai. So here we investigated how biochar influence vegetation growth over a period of like 2 years, and also studied hydraulic conductivity performances in soil plant composites over 2 years of biochar implementation. So biochar is found to suppress hydraulic conductivity by forming some root hair soil composite through its mucilage. So these are kind of interaction studies that we need in future. So this is just published for 2 years. So, but we, as I said, we need even for longer duration and also to understand the potential of this material. So I'd like to thank for this presentation also and collaboration in related aspects with Professor Shrideep from IIT Guwahati. I think he's given wonderful lecture yesterday. Dr. Beretta from University of Leeds, Dr. Ajit Sharma, who is also very pioneer in biochar applications, and Dr. Bodolai from Hong Kong USG for design of biochar in Infleunce. So I would like to thank you and also have some discussion. Yeah, thanks.
Yeah, so thank you, Dr. Ankit, for taking the time and giving a detailed presentation on the biochar. So I think so you won't get anything outside this much elaboration of presentation of biochar anywhere else. So thank you. So I now request the present participants just to unmute and pose a question. But there was one question already in the chat box. What is the range of temperature for the pyrolysis to take place? Is it controlled pyrolysis?
Okay, yeah. So for the range of temperature, when it's a pyrolysis process, so pyrolysis is the process by which we produce biochar from biomass. So when I say about temperature, so temperature we can control it. Okay, I mean there are two methods. One is we can using control method. So in this we can control temperature either. I mean usually we control it from 300 degrees Celsius up to 700 degrees Celsius for most of the biomass. But in some cases, we can also go beyond 700 degrees Celsius to 1000 degrees Celsius. But in most of the cases, we control the temperature. That is true. So it depends on our purpose. Where we want to make biochar at 300 degrees Celsius. We want to make it 500 degrees Celsius or 700. That is totally up to us. Yeah.
So there's another question. Can a life cycle analysis be carried out on different types of biochars?
Life cycle analysis. Okay. There has been some literature on life cycle analysis of biochar. But for that, I think, again, we need to also think about application side. If we have to think about application, suppose in landfill liners, etc. Currently, we don't have the data yet, full data yet, of how this biochar will, how the landfill liners will perform under influence of these biochars for long term. So there are life cycle analysis, but not with respect to this particular application. So, but we need, as I said, this is currently in research stage. So we need to have a lot of field data first before we go into life cycle analysis of how the system will perform with presence of this biochar. Yeah.
So another question: can we use it in a bottom liners also with the bentonite soil if it is in hazardous waste?
Uh, in with bentonite, I mean, there have been studies published. I mean, biochar, okay, in one way it can reduce the swelling of bentonite to some extent, and also it helps to soak some contaminants. But it is not very active material biochar for, uh, especially for if you're talking about hazardous material, hazardous waste. So I do not think biochar can be recommended for that part. But if you want to think only about the swelling part, to contain swelling, etc., it's okay. But if you want to think about hazardous waste, I think no. Yeah.
The last question. So
Mhm.
can you please explain about biochar and water interaction?
Okay. Um, I think one diagram I will show it again. So when you say biochar and water interaction, okay. So this is very basic. I think I mean, always seen unsaturated soil mechanics. So, I mean, biochar is also a kind of soil material. Okay? It's also a porous material like a soil. So when I say biochar water interaction, so biochar can interact water in, I mean, two major ways. One is it can hold water in its pores, just like soil hold in its pores. So assume soil is a biochar here. And there is another way the biochar can hold water is through its surface functionality, um, which is which is through this one. So through this OH groups, so it can also hold water molecules. In addition to these pores, it can also hold water molecules through this way. So these are two major ways how biochar interact with water. Yeah.
Uh, okay. So the
This one,
last question is any effects on long-time cementation properties?
long-term cementation. Um, biochar itself don't have. It's not like fly. I mean, I know fly ash, and when you mix with lime, you have cementation effect. Biochar itself don't have any itself have true cohesion. Okay, so biochar don't have any own cementation. However, there has been studies where if you mix biochar specifically, which have a lot of calcium content inside, okay, they can generate some cementation when you mix with expensive soil, some particular expensive soil. But in itself, biochar don't have any cementitious effect. So the word which I use, soil biochar aggregates, they are very temporary, you can say in nature, depending of course on the water content. And the other type of aggregates which I talk about is soil root uh, biochar aggregate, which is formed because of root mucilage. Now, root mucilage is also cementatious in nature, but the effect is much less than true cementation that we are talking about. So the cementatious part in biochar is very minimal. Okay, you may even neglect it. Yeah,
Thank you, Dr.
yeah.
Ankit,
Thanks.
so for
Yeah.
generously accepting our
Welcome.
invitation
Mm,
and delivering the presentation.
yeah. Thank you very much. Yeah.
Yeah. So if anybody
Sir.
has any, hello.
Yes. Hello, sir. Good
Yes.
afternoon, sir. Sir, Manas here, Manas Chandan Mishra from IIT Bhubaneswar. Sir,
Yes. Yes.
I have come across few studies who have demonstrated that biochar can be effectively used to reclaim acidic soil due to its adsorption capacity.
Mm-hmm.
It helps to absorb some leaching out metals and others, and it
Mm-hmm.
helps in increasing the pH. So, has there
Mm-hmm.
been any instances where biochar can be used in um, leaching some toxic element, potentially toxic elements, or to reduce the alkalinity as well? In any of these cases, can have you ever
No, there
have?
are a lot of studies on biochar on heavy metals absorption. There are a lot of studies, especially in wastewater treatment. Too many studies are there. Even in soil cases, there are. But the problem is there are mostly laboratory studies, and the major problem is if you want to use in the field, I mean, uh, you can use it to reduce maybe contamination in the soil in some form. But the problem is the long-term usage. Okay, uh, when you mix in the field in this biochar, how will you maintain it for long term? okay, so that it keeps on reducing the contamination. That is one problem. So there are a lot of studies on biochar reducing this heavy metal, I mean, from wastewater also, and even from soil. But I think the problem is taking it to the field level, the same with the biochar. Because once you remove it, it itself takes that metal to its surface, okay, and further its extraction may not be very easy if you want to reuse it again. So that is one problem.
Thank you, sir.
Yeah.
Thank you. Thank you, Dr. Ankit.
Yeah,
So,
thank you very much.
Yeah.
Yeah.
So, can you unshare the slides?
Oh, okay. Yeah, yeah, thanks.